Welcome to the deep dive. We're here to really get into complex topics, pull out the key ideas, and, well, give you the shortcut to being genuinely informed. Today, we're diving into something pretty fundamental, the laws that govern, well, everything. From Galileo, Einstein's relativity, quantum electrodynamics, physics is always searching for these universal rules.
It really is. And we've had incredible success, especially with forces like gravity and electromagnetism, the long-range ones we sort of experience daily.
Right, you can feel gravity, see light. But then there's this other world, isn't there? The short-range interactions.
The weak and strong forces, things
Mhm.
like radioactive decay, what holds the nucleus of an atom together.
And for ages, understanding those within a consistent theory was a huge headache, a real puzzle.
Absolutely. We had these beautiful symmetric theories for the long-range forces, but the short-range ones just didn't fit neatly. So today's deep dive, it's all about how this incredible idea, the BEH mechanism developed independently by Englert, Brout, and Peter Higgs, basically unlocked the standard model. It explained how particles get mass, predicted this scalar boson, which was finally found at CERN years later. If you appreciate the elegance of physics, this story is really something. The fundamental problem, mass and symmetry in particle physics.
Okay, so to really get why this BEH mechanism was such a breakthrough, we need to set the stage. What was the actual problem they were trying to solve?
Well, you mentioned the long-range forces, gravity, electromagnetism.
Yeah, the ones we can sort of see or feel without fancy equipment.
Exactly. And our theory for electromagnetism, quantum electrodynamics, or QED, it's built on something called local symmetries. And the amazing thing about QED is it works perfectly at the quantum level. Incredibly precise predictions, verified experimentally.
Unlike classical general relativity, which also has local symmetries but isn't quite a full quantum theory yet.
Right. And that quantum consistency of QED, that's the gold standard. We wanted that for the other forces too.
So the natural step was to generalize QED.
Precisely. That led to what we call Yang-Mills theory. Same idea. Local symmetries, force carriers called gauge vector bosons, kind of like generalized photons.
Okay, sounds good so far. But these Yang-Mills theories, just like QED, they naturally have massless gauge bosons, right? Like the photon is massless.
Exactly.
Oh.
And there's the rub. To make an interaction short range, the particle carrying that force needs to have mass.
Because a massive particle limits the range. It's like the range is roughly Planck's constant divided by the mass times c. So heavier particle, shorter range.
You got it. So we needed mass for the carriers of the weak force, for instance. But the theory, the very local symmetry that made QED so successful,
It seemed to forbid giving mass to these gauge bosons.
it did. If you just try and stick a mass term into the equations by hand, you wreck the symmetry. You lose that beautiful consistency, the predictability, the renormalizability that makes QED work.
So the huge question was, how did these force carriers get mass for short-range interactions without breaking the underlying symmetry? That sounds
Yeah.
tricky.
It was the central theoretical challenge for decades. 2. The seed of the solution, spontaneous symmetry breaking, SSB.
Okay, so how did they crack it? The solution came from a slightly mind-bending idea, didn't it? Spontaneous symmetry breaking.
That's the one, SSB. The core idea is, what if the fundamental laws, the dynamics, are perfectly symmetric, but the actual state of the system, the ground state or vacuum, isn't
This itself sort of chooses an asymmetric state.
exactly. It spontaneously breaks the symmetry. And this wasn't totally new. It was actually a well-known concept in statistical physics. Think phase transitions.
Right, like in condensed matter physics, you see this stuff all the time.
You do. Ground states often become ordered. They pick up some order parameter that symmetry alone would say should be zero. Happens a lot in second-order phase transitions. And it was Yuichiro Nambu who really brought this idea across from condensed matter into particle physics, into relativistic quantum field theory.
So let's use an analogy, maybe. Ferromagnetism, that's the classic one, isn't it?
Perfect example. You take a chunk of iron. Above a certain temperature, the Curie temperature, it's not magnetic. The little atomic magnets point every which way. Symmetric.
Okay.
But cool it down below TC, and bam, they all line up. The whole thing becomes a magnet, pointing in some specific direction.
Even though the underlying laws governing those atomic magnets don't prefer any particular direction, they're rotationally symmetric.
Precisely. The system spontaneously chose a direction.
Yeah.
And this shows key features of SSB. First, degeneracy.
Right.
Once it picks north, Say, it could have picked south or east or any other direction. Infinite equivalent ground states.
Okay, makes sense.
Second, you get massless excitations. If you nudge the magnetization slightly sideways, perpendicular to the chosen direction, it costs almost no energy. These are like ripples, spin waves, or quantical magyons. They're massless modes.
And third?
Third, if you try to change the magnitude of the magnetization, push along the direction it chose, that does cost energy. That corresponds to a massive mode. It reflects the stiffness, the rigidity of the order.
You can picture this with that Mexican hat potential, right?
Yeah.
Above TC, just one minimum at 0. Below TC, a brim, a valley of minima.
Exactly. The system rolls into the valley, picking a spot. Moving along the valley floor is massless. Climbing the sides is massive.
So ferromagnetism shows the basics, but you mentioned superconductivity was even more relevant.
Yeah, superconductivity adds a crucial twist. There, you also have SSB, a quantum phase symmetry, is broken by electron pairs condensing.
Okay.
Now, if it were just that, you'd expect a massless mode like the magyons. But superconductors are typically charged systems, and you have the long-range electromagnetic force, the Coulomb interaction involved.
Ah, so electromagnetism changes things.
It does. That long-range interaction effectively eats the massless mode. It disappears from the spectrum and instead gets incorporated into making the photon behave as if it has mass inside the superconductor. This gives rise to a massive plasma mode.
Wow. So the massless mode vanishes, and a massive mode appears instead, tied to the long-range force.
Exactly. And that phenomenon, sometimes called the Anderson-Higgs mechanism in condensed matter, was a direct precursor to what happens in particle physics.
And Nambu saw this connection from superconductivity theory, like BCS theory, to particle physics.
He did. Brilliant insight. He applied SSB to chiral symmetry in particle physics. He showed how a fermion condensate could generate mass for fermions, and crucially, it also predicted a mathless particle, a pseudoscalar.
Which turned out to be related to the pion.
Yes, it explained why the pion is so light compared to other strongly interacting particles. A huge breakthrough. That massless particle is the field theory version of the magnon, the spin wave. Then Jeffrey Goldstone developed a simple model field theory that really clarified this.
The Goldstone model, with that potential, again, like the Mexican hat.
Right, a potential with the symmetry. Say you want like rotations in a circle. The minimum isn't at the center, zero field, but somewhere out on the circle. The system picks a point on the circle.
Breaking the symmetry.
And when you look at quantum fluctuations around that minimum, you get two types. One is massive, that's like oscillating up and down the side of the hat brim.
That's phi1 in the diagrams.
Right. And the other is massless, that's oscillating along the brim around the circle. That's phi2. These massless ones are the Nambu-Goldstone bosons, or Ng bosons. 3, the BEH mechanism, giving mass to gauge bosons.
Okay, so SSB creates these massless Ng bosons, but that's for global symmetries, where the symmetry operation is the same everywhere. What happens when you make the symmetry local? Like electromagnetism, where the symmetry can change from point to point in space-time.
Ah, now we get to the heart of it. To make a symmetry local, you have to introduce a gauge field, like the photon field R for QED's local U1 symmetry.
So you gauge the symmetry. What does that do to the Nambu-Goldstone boson, the field that runs around the valley floor?
This is the crucial step. Remember, moving along that valley corresponds to just rotating the direction of the field in that internal symmetry space. But with a local symmetry, those rotations are precisely the gauge transformations.
Meaning they're not real physical changes.
Exactly. Because of gauge invariance, particularly the gauge invariance of the vacuum state, those fluctuations along the valley, the V2 mode, are just different mathematical descriptions of the same physical state. They become redundant.
So the massless Nambu-Goldstone boson, it just vanishes from the list of actual physical particles.
It disappears from the physical spectrum. It's effectively absorbed.
Okay, hang on. If a degree of freedom just disappears, where does it go? Physics usually doesn't like things just vanishing.
It doesn't vanish. This is the genius of the VEH mechanism. That degree of freedom, the one corresponding to the Ng boson, gets transferred to the gauge field.
The Au field. How?
Think about a massless gauge boson, like the photon. It only has two physical polarizations, transverse ones, like light waves oscillating perpendicular to their direction of travel.
Right.
But a massive vector particle needs three polarizations. It needs that third one, the longitudinal polarization, kind of like a sound wave compressing along its direction of travel.
And the Ng boson provides that missing piece.
Precisely. The gauge field eats the Nambu-Goldstone boson, and uses its degree of freedom to become the needed longitudinal polarization. And by gaining that third polarization, the gauge field becomes massive.
Wow. So the symmetry breaking provides the vacuum structure. The gauge field interacts with it, eats the Goldstone boson, and gets mass. That's the BEH mechanism.
That's the core of it. You can see in the Feynman diagrams. The gauge field propagates through this vacuum, which isn't empty, but has this scalar field condensate, this non-zero expectation value, you say. This interaction gives the gauge field apple a mass term, and the mass squared is proportional to the coupling squared times the c squared.
And crucially, this happens without breaking the local gauge symmetry explicitly.
Yes, that's the magic. The underlying symmetry is still there, hidden. It manifests in relationships called ward identities, which ensure the theory remains consistent, predictive, renormalizable.
So it fixes the mass problem and keeps the theory mathematically sound.
Exactly. And depending on how the symmetry breaks, which parts of the scalar field get a vacuum value, you can arrange for some gauge bosons to get mass, like the W and Z, while others, like the photon, remain massless. It depends on the specific pattern of symmetry breaking.
Okay, so the massless phi gets eaten. What about the other one from the Goldstone model, the massive phi, the one climbing the potential wall? Does it get eaten too?
No, that one survives. Fluctuations in phi1 correspond to changing the magnitude of the condensate, stretching the field value. That's a real physical gauge invariant change.
So the BEH mechanism predicts not only massive gauge bosons, but also the existence of a leftover massive scalar boson.
Yes, that surviving massive scalar, phi1, is a key prediction. And its couplings are also predicted how strongly it interacts with the now massive W and Z bosons, and also how it interacts with fermions.
Fermions, like electrons and quarks, how do they get mass?
Through this same scalar field. The fundamental fermions couple to the scalar field. When phi gets its non-zero vacuum expectation value, EIS, that coupling turns into a mass term for the fermion. So electron mass, quark masses, they all arise from interacting with this pervasive scalar field background.
So this mechanism seems incredibly powerful. It solves the gauge boson mass problem, predicts a new scalar particle, explains fermion masses. Why was it considered so essential, though? Couldn't there have been other ways?
The fundamental reason is quantum consistency, renormalizability. Before BEH, trying to describe the weak force with massive W and Z bosons just didn't work reliably when you calculated quantum corrections. You got infinities you couldn't systematically remove.
The theory wasn't predictive at high energies.
Right. The BEH mechanism, by generating mass through SSB while preserving the underlying local symmetry, ensures that the theory is renormalizable. Proving this was incredibly difficult. 't Hooft and Veltman earned a Nobel Prize for it, but it showed the standard model built on BEH was a mathematically sound predictive quantum field theory. That was absolutely vital. 4. The triumph. BEH in the standard model and the discovery at CERN.
And the place where this mechanism really shone was in building the standard model, specifically the electroweak theory, right? Unifying weak and electromagnetic forces.
Yeah, absolutely. It's the cornerstone. The standard model lists all the known fundamental building blocks. You have the matter particles, the fermions, electrons, neutrinos, quarks, grouped into 3 generations. Then the force carriers, the gauge bosons, the photon for EM, the W plus, W and Z for the weak force, and 8 gluons for the strong force. And crucially, 1 massive scalar boson predicted by the BEH mechanism. Without the BEH effect, without that scalar field having a non-zero value in the vacuum, the WZ and all the fermions would be massless.
So it's the BEH mechanism giving mass to the W and Z, electrons, quarks, but leaving the photon and gluons massless.
Correct. The specific way the symmetry breaks in the standard model achieves exactly that. Gluons remain massless but get confined, making the strong force short range through a different, more complex, non-perturbative effect. But for the weak force and fermion masses, it's BEH.
The theory was incredibly successful. Predicted the W and Z bosons, their masses were measured in the 80s at CERN, matching predictions. But finding that scalar boson itself took a lot longer.
It did. It was the missing piece for decades. The search was long and incredibly challenging. The standard model predicts how this scalar boson, let's call it H, should interact. It couples most strongly to heavy particles, so to W and Z bosons and the top quark.
And its coupling to photons is indirect, through quantum loops.
Exactly. It doesn't couple directly to massless photons, but it can interact via virtual loops of W bosons or top quarks. So finding it required a machine powerful enough to produce it and detectors sensitive enough to see its decay products.
Enter the Large Hadron Collider, the LHC, at CERN.
The LHC, a truly monumental machine, That 27-kilometer ring smashing protons together at enormous energies, 8 TeV initially, now even higher. And the collision rate is just mind-boggling, almost a billion per second.
Why such high energy and rates?
You need the energy to create a particle with a mass around, well, what turned out to be 125 in GeV. And you need the high rates because the scalar boson is actually quite rare, and its decay modes into clean signatures are even rarer. You have to sift through mountains of data.
So what was the smoking gun? How did they know they'd found it?
There were several key decay channels they looked for. One of the cleanest, though rare, was the decay into two Z bosons, which then decay into pairs of leptons, like electrons or muons. So you look for 4 leptons coming from the collision point.
And they saw an excess.
They saw a clear bump.
Yeah.
If you plotted the number of 4 lepton events versus the combined energy or invariant mass of those leptons, both the ATLAs and CMS experiments saw a distinct peak rising above the expected background, right around 125, 126 GeV.
That red curve in the famous plots.
That's the one. Seeing that peak emerge in different decay channels, like decay into 2 photons as well, and measuring its properties like its spin, which had to be 0, as predicted for this scalar, the evidence became overwhelming. It matched the predictions for the standard model scalar boson beautifully.
Finding it must have been incredible, not just confirming a theory, but finding a fundamentally new kind of particle.
It was monumental. Think about it. Every other fundamental particle we knew had spin 12 fermions, spin 1 vector bosons. This was the first ever elementary particle discovered with spin 0.
Wow.
Its discovery really cemented the standard model. And the fact that it appears to be elementary, as described in the simplest version of the BEH mechanism, rather than some composite object emerging from a new strong force, has really profound implications. It shapes how we think about physics at even higher energies, maybe pushing towards the Planck scale, where gravity becomes quantum. It was truly a capstone discovery.
So what a journey. From this deep theoretical problem, how do force carriers get mass without breaking fundamental symmetries through this counterintuitive idea of spontaneous symmetry breaking borrowed from condensed matter?
To the elegance of the BEH mechanism, how it gives mass not just to gauge bosons, but to fermions too, predicts this unique scalar particle.
And then the incredible experimental effort culminating in finding that particle at CERN, confirming the whole picture.
It really shows this amazing interplay between symmetry, the quantum vacuum, and the fundamental properties of particles. How the vacuum itself isn't empty but structured, and that structure gives mass to everything around us.
The existence of this elementary scalar, consistent with the standard model, it feels like both an ending and a beginning. It completes the model, but also points towards, well, what's next?
Exactly. So maybe something for you, the listener, to think about. Now that we have this elementary scalar field confirmed, how does that influence our search for physics beyond the standard model? Does understanding how mass arises at the electroweak scale give us clues about physics at much higher energies, maybe even near the Planck scale where quantum gravity might finally come into play? What other secrets might this scalar field hold?